All right, so this is the second part of 8.3 part 2. The first part we went through and went over word problems involving the dropped/thrown objects formula. And now we are going to go ahead and just review miscellaneous stuff from 8.3, where you are finding all real and imaginary solutions to the equations. So, in this problem here, my first thought would be, if I'm going to solve this, then I would try to factor it if I can. I always try to factor first. Remember, you can only use x equals opposite of b plus or minus square root quantity b squared minus 4ac all over 2a. You can only use this if the highest exponent equals 2. So in this one, my highest exponent is 4, so I can't do that. So you should always try to factor then. So when I look at this problem, I look for my GCF first. Always, always, always look for a GCF. So is there a number that divides into 3 and 48 evenly? And there is. It's 3. So I'm going to pull out a 3. We can divide each one of these by 3, and we'd get x to the 4th. And 48 divided by 3 is negative 16 equals 0. Now, even though my exponent here is not a 2, and remember, when it's not a 2, we have to treat things a little bit differently, right? But there are only 2 things. So when I look at it, if there's only 2 terms, we have to look for difference of squares. So we have to think, is x to the 4th a perfect square? And it is, because it's an even exponent, and so is 16 a perfect square. So we can break this up into their roots. X to the 4th splits up evenly into x squareds. 16, the root of 16 is 4. 1 positive, 1 negative. Remember your GCF out front. Now you have to try to factor this again. So again, there's only 2 of them, so we should be looking for perfect squares if there are any. So x squared is a perfect square, so is 4, but they have to be having their differences, and this is not, so it would stay x squared plus 4, and I still bring down my GCF of 3. These are perfect squares, and there is a minus sign between, so we can go ahead and split that up to x plus 2, x minus 2 equals 0, right? And then we can go ahead and set each piece equal to 0. Well, 3, we can set it equal to 0, but you can't solve for x, so that doesn't matter. So x squared plus 4 equals 0, x plus 2 equals 0, and x minus 2 equals 0. So these we can solve quickly. Just add 2. X would equal 2 is one of your answers. Subtract 2. X equals negative 2 is another answer. And this one we're actually going to have to solve for x squared, so we're going to subtract the 4. And we get x squared equals negative 4. Then remember, to get rid of a square, the opposite of squaring something is taking the square root. And here you just took an even root. So there should be 2 solutions. So this will be positive or negative. And then when we go to split this up, right, square root negative 1, square root 4. Well, square root of 4 is 2. The square root of negative 1 is I. So positive or negative I. And just like my highest exponent was 4 here, I have 1, 2, 3, 4 solutions. So my solutions are negative 2, positive or negative 2i, and 2. All right, looking at number 2, same basic idea here. We have an exponent of 4, so I'd look for a GCF first and try to start factoring, right? If my exponent's not 2, I should try to factor. So since it's 4, I'm going to try to factor it. There is no GCF here, but 81 is a perfect square, and 1 is a perfect square, so we can break those up because there is the difference of perfect squares here. So the square root of 81 is 9. M to the 4th breaks up into m squared, right? Because we have to break 4 up into 2 pieces evenly. Square root of 1 is 1, one of them positive, one of them negative. Then I would try to factor this again. So there are only 2 terms. They both have to be perfect squares. Well, 9 and 9's a perfect square, m squared is a perfect square, and so is 1. But this has a plus sign, so we cannot split it up. They have to stay together. So it'd be 9m squared plus 1. Here, these are perfect squares, but now they're having their differences, so we can break them up. And the root of 9m squared is 3m, and the root of 1 is 1. 1 is positive, 1 is negative, equals 0, and then we can go to set each piece equal to 0, and solve. So subtract the 1, 9m squared equals negative 1, divide by 9, m squared equals negative 1/9, and now we're going to square root. But again, remember, the minute you take an even root, there's going to be two solutions, a positive and a negative, right? And don't forget this, right? This is really saying the square root of negative 1 over the square root of 9. And isn't the square root of negative 1 I, and the square root of 9 3? So m is equal to a positive or negative I over 3. Those are your first two solutions because of the positive and negative piece. Then we can go ahead and solve this other one. Subtract 1, so you'd have 3m equals negative 1. Divide by 3. M equals negative 1/3 is your other solution. And then the last one, we would add 1 to get rid of subtracting it. So 3m equals 1. Divide by 3. M equals positive 1/3 is your last solution. So your solutions to these are negative 1/3, positive or negative, I over 3, and 1/3. Okay. Next problem, same sort of idea, right? Our exponent is not a 2, it's a 4, so we're going to have to factor this, right? There is no GCF. In this one, there's 3 terms, and my first term is 1, so since my a equals 1, I can think about what multiplies to the last, negative 144, and adds to the middle, which is 7. So I'd need to sit there and think about that, right? So maybe I'll pull out my calculator and say, oh, well, let's try this, because 144 divided by 2 would be 2 and 72. That doesn't work, because there's no way to combine those to that. So 144, I know 12 goes into there 12 times, but then that would cancel out and give me 0, so I can't use the 12s. So 144 divided by 3, so 3 and 48. Can't get 7 by either adding or subtracting those. How about 4? Well, 4 and 36, but I can't add or subtract those to get 7. I know 5 won't work because it doesn't end in a 5 or a 0, so then I can try 6. 6 goes in there 24 times, but if I add them, it's 30. If I subtract, it's 18. 7 doesn't work. 8 goes in there 18 times. That's close because I could get to 10 if I subtract, but still no good. 9 goes in there 16 times. Well, let's see. 16 minus 9 is 7. So if the 9 is negative, then we would get there. So here's our two numbers. So this breaks up into n minus 9, n plus 16 equals 0. And don't forget, our exponent was not a quadratic, so we have to take whatever the exponent was here and put that in as our exponent here. So our middle term was a squared, so these are squareds. Now that we have two terms, we have to look for perfect squares. Well, n squared is a perfect square, 9 is a perfect square, and they are having their differences. So I can split this up into n plus 3 and n minus 3. These are both perfect squares, but there's an addition sign here, so I cannot split that up. And then we need to set each piece equal to 0. I'll put that one down a little further so I have more room to work. And then we need to solve those. So here we can subtract 3. N equals negative 3 is one of my answers. Add 3. N equals 3 is another answer. And this one we're going to have to go a little bit further with. So we are going to subtract the 16. And we'd have n squared equals negative 16. Now we are going to need to square root this. And remember, even root means two solutions. So this will be positive or negative. And then when we split this up into negative 1 and 16, The square root of negative 1 is I. The square root of 16 is 4. So n equals positive or negative 4i. So my solutions are negative 3, positive or negative 4i, and positive 3, which could also be written as positive or negative 3 and positive or negative 4i. I will accept either answer. Just realize that since these are both a positive and a negative, it can be written in either format. And the last one we're going to go over together is number 4. So when we look at number 4, first thing we should do is it is a square, so I could use the quadratic formula on it, but I like to try to factor first. And here there is no GCF, and there's only 2 terms, so I need to see if they're having a difference of perfect squares. And in this case, they are not having their differences because it's a plus sign, so I can't break it up. So I'm just going to have to solve it. So I would subtract 25. We would get w squared equals negative 25 square root. Again, the minute you take a square root, you should realize even root means 2 solutions. So this will be positive or negative, and when I split it up into square root of negative 1, square root of 25, so this will be positive or negative 5i, because the square root of 25 is 5, the square root of negative 1 is I. These would cancel, leaving with w equals positive or negative 5i. So my solution is just positive or negative 5i. And I did get 2 solutions with an exponent of 2, so I know I'm on the right track. All right, so now you have 3 more to try on your own at the bottom. So make sure you try these on your own before you come into class tomorrow so that I can answer your questions on them at that time.